A human's lifespan, disease risk, and physiological baseline are calibrated months before they are born. Over the last few decades, epidemiological studies have found that cardiovascular disease, metabolic syndrome, and psychiatric disorders frequently cluster in adults who shared a specific prenatal history. The primary clinical proxy for this history is intrauterine growth restriction, or low birth weight. This correlation is continuous across the entire range of normal birth weights. As the data points move toward lower birth weights, the risk of adult hypertension and type 2 diabetes rises in a predictable, dose-dependent curve. These associations remain statistically significant even after correcting for postnatal factors like adult obesity or socioeconomic status. Rather than accidental damage or simple nutrient deficiency, the fetus adjusts its development in response to specific chemical signals from the mother. The driver of this shift is an overexposure to maternal stress hormones. This is developmental programming. When maternal stress hormones breach the placenta, they can rewrite the fetal epigenome and permanently alter the body's stress feedback loop. Under normal conditions, maternal glucocorticoid levels are significantly higher than those in the fetal circulation. The placental capillary interface serves as the anatomical boundary where the fetus must be protected from the high concentrations of stress hormones circulating in the mother's blood. This protection is maintained by an enzyme called 11-beta-hydroxysteroid dehydrogenase type 2, or 11-beta-HSD2. These enzymes line the placental barrier and intercept active stress hormones like cortisol or corticosterone before they can enter fetal circulation. 11-beta-HSD2 inactivates these hormones, converting them into inert forms like cortisone. However, severe maternal stress, hypoxia, or protein restriction can downregulate the production of this enzyme. When 11-beta-HSD2 expression drops, the barrier fails, and active glucocorticoids flood the fetal system. This exposure to active hormones initiates the metabolic shift that restricts fetal growth and begins rewiring the brain. Once they cross the placental barrier, these excess glucocorticoids travel into the developing fetal central nervous system. They target the hippocampus, a region highly sensitive to hormone levels during its formative stages. The presence of these hormones during this critical window triggers a series of stable epigenetic modifications. The molecular target is the promoter region for the glucocorticoid receptor gene at exon 1-7. The first modification is DNA hypermethylation. Methyl groups bond to the sequence, creating a chemical obstruction preventing gene activation. This is followed by histone hypoalphetylation, which causes the DNA strand to wind tightly and condense into a dense, inaccessible structure. Because the chromatin is so tightly packed, transcription factors like NGFIA are physically unable to reach the DNA. This permanent silencing of the gene ensures the brain is built with a deficit of the receptors required to sense and regulate stress. We can see the consequences of this missing hardware by looking at the hypothalamic-pituitary-adrenal, or HPA, axis. To maintain homeostasis, the HPA axis relies on negative feedback. It must sense when it has produced enough cortisol to signal the system to stop. In a healthy system, shown in panel A, glucocorticoid receptors in the hippocampus detect rising cortisol and signal the hypothalamus to cease production. This feedback requires high receptor density to efficiently catch cortisol and trigger the braking signal. But in the programmed state, that sensing capability is gone. In panel B, ethicanax silencing leaves the brain with a lower receptor count, weakening the inhibitory signal and cutting the axis's brakes. Without feedback, the hypothalamus and pituitary continuously pump out stress hormones, leading to chronic elevations in CRH and ACTH. The organism is now locked into a state of chronic, mild HPA axis hyperactivity that persists throughout adulthood. This flowchart tracks how maternal environment alters lifelong physiology. To survive inputs like poor nutrition or stress, the fetus adapts by prioritizing metabolic efficiency. While aiding survival in utero, these shifts translate directly into the adult phenotype, increased risk for cardiovascular disease and diabetes. Chronic cortisol exposure forces the liver to constantly output glucose via enzymes like PEPCK. Constant glucose production eventually leads to insulin resistance and metabolic syndrome. The fetal epigenome treats high maternal stress as a prediction of a high-risk, calorie-poor environment. In that context, prioritizing rapid stress responses and aggressive calorie storage is a survival strategy. This is the thrifty phenotype, a body built for hypervigilance and survival in a starved world. Adult disease occurs when this scarcity-adapted body is forced into a modern environment where resources are rich